The next few videos are about using the backpropagation algorithm to learn a feature representation of the meaning of a word. I'm going to start with a very simple case from the 1980s when computers were very slow. It's a small case, but it illustrates the idea about how you can take some relational information and use the backpropagation algorithm to turn relational information into feature vectors that capture the meanings of words. This diagram shows a simple family tree in which, for example, Christopher and Penelope marry and have children Arthur and Victoria. What we'd like is to train a neural network to understand the information in this family tree. We've also given it another family tree of Italian people, which has pretty much the same structure as the English tree. And perhaps when it tries to learn both sets of facts, the neural net is going to be able to take advantage of that analogy. The information in these family trees can be expressed as a set of propositions if we make up names for the relationships depicted by the trees. So we're going to use the relationships son, daughter, nephew, niece, father, mother, uncle, aunt, brother, sister, and husband, wife. And using those relationships, we can write down a set of triples, such as Colin has father James, Colin has mother Victoria, and James has wife Victoria. And in the nice simple families depicted in the diagram, the third proposition follows from the previous two. Similarly, the third proposition in the next set follows from the previous two. So the relational learning task, that is, the task of learning the information in those family trees, can be viewed as figuring out the regularities in a large set of triples that express the information in those trees. Now, the obvious way to express the regularities is as symbolic rules. For example, X has mother Y and Y has husband Z implies X has father Z. We could search for such rules, but this would involve a search through quite a large space, a combinatorially large space, of discrete possibilities. A very different way to try and capture the same information is to use a neural network that searches through a continuous space of real valued weights to try and capture the information. And the way it's going to do that is we're going to say it's captured the information if it can predict the third term in a triple from the first two terms. So at the bottom of this diagram here, we're going to put in a person and a relationship, and the information is going to flow forwards through this neural network, and what we're going to try and get out of the neural network after it's learned is the person who's related to the first person by that relationship. The architecture of this net was designed by hand. That is, I decided how many layers it should have, and I also decided where to put bottlenecks to force it to learn interesting representations. So what we do is we encode the information in a neutral way. There are 24 possible people, so the block at the bottom of the diagram that says local encoding of person 1 has 24 neurons, and exactly one of those will be turned on for each training case. Similarly, there are 12 relationships, and exactly one of the relationship units will be turned on. And then for a relationship that has a unique answer, we would like one of the 24 people at the top, one of the 24 output people, to turn on to represent the answer. By using a representation in which exactly one of the neurons is on, we don't accidentally give the network any similarities between people. All pairs of people are equally dissimilar. So we're not cheating by giving the network information about who's like who. The people, as far as the network are concerned, are uninterpreted symbols. But now in the next layer of the network, we've taken the local encoding of person 1 and we've connected it to a small set of neurons. I actually use 6 neurons for this. And because there are 24 people, it can't possibly dedicate 1 neuron to each person. It has to re-represent the people as patterns of activity over those 6 neurons. And what we're hoping is that when it learns these propositions, the way in which it encodes a person in that distributed pattern of activity will reveal structure in the task or structure in the domain. So what we're going to do is we're going to train it up on 112 of these propositions, and we go through the 112 propositions many times, slowly changing the weights as we go, using backpropagation. And after training, we're going to look at the 6 units in that layer that says distributed encoding of person 1 to see what they're doing. So here are those 6 units as the big grey blocks. And I laid out the 24 people with the 12 English people in a row along the top and the 12 Italian people in a row underneath. So each of these blocks, you'll see, has 24 blobs in it, and the blobs tell you the incoming weights for one of the hidden units in that layer. So going back to the previous slide, if you look at that layer that says distributed encoding of person 1, there are 6 neurons there, and we're looking at the incoming weights of each of those 6 neurons. If you look at the big grey rectangle on the top right, you'll see an interesting structure to the weights. The weights along the top that come from English people are all positive, and the weights along the bottom are all negative. That means this unit tells you whether the input person is English or Italian. We never gave it that information explicitly, but obviously it's useful information to have in this very simple world, because in the family trees that we're learning about, if the input person is English, the output person is always English. And so just knowing that someone's English already allows you to predict one bit of information about the output, which is equivalent to saying it halves the number of possibilities. If you look at the grey blob immediately below that, the second one down on the right, you'll see that it has 4 big positive weights at the beginning. Those correspond to Christopher and Andrew, or their Italian equivalents. Then it has some smaller weights. Then it has 2 big negative weights that correspond to Colin, or his Italian equivalent. Then there's 4 more big positive weights corresponding to Penelope or Christine, or their Italian equivalents. And right at the end, there's 2 big negative weights corresponding to Charlotte, or her Italian equivalent. By now you've probably realised that that neuron represents what generation somebody is. It has big positive weights to the oldest generation, big negative weights to the youngest generation, and intermediate weights that are roughly 0 to the intermediate generation. So that's really a 3-valued feature, and it's telling you the generation of the person. Finally, if you look at the bottom grey rectangle on the left-hand side, you'll see that has a different structure. And if we look at the top row and we look at the negative weights in the top row of that unit, it has a negative weight to Andrew, James, Charles, Christine and Jennifer. And now if you look at the English family tree, you'll see Andrew, James, Charles, Christine and Jennifer are all in the right-hand branch of the family tree. So that unit has learned to represent which branch of the family tree someone is in. Again, that's a very useful feature to have for predicting the output person, because if you know it's a close family relationship, you expect the output to be in the same branch of the family tree as the input. So the networks in the bottleneck have learned to represent features of people that are useful for predicting the answer. And notice we didn't tell it anything about what features to use. We never mentioned things like nationality or branch of family tree or generation. It figured out that those are good features for expressing the regularity in this domain. Of course, those features are only useful if the other bottlenecks, the one for relationships and the one near the top of the network before the output person, use similar representations, and the central layer is able to say how the features of the input person and the features of the relationship predict the features of the output person. So, for example, if the input person is of generation 3 and the relationship requires the output person to be 1 generation up, then the output person is of generation 2. But notice, to capture that rule, you have to extract appropriate features at the first hidden layer and the last hidden layer of the network, and you have to make the units in the middle relate those features correctly. Another way to see that the network works is to train it on all but a few of the triples and see if it can complete those triples correctly. So does it generalize? So there's 112 triples, and I trained it on 108 of them and tested it on the remaining 4. I did that several times, and it got either 2 or 3 of those right. That's not so bad for a 24-way choice. So it's true it makes mistakes, but it didn't have much training data. There's not enough triples in this domain to really nail down the regularities very well. And it does much better than chance. If you train it on a much bigger data set, it can generalize from a much smaller fraction of the data. So if you have thousands and thousands of relationships, you only need to show it a small percentage before it can start guessing the other ones correctly. That research was done in the 1980s and was a way of showing that backpropagation could learn interesting features. And it was a toy example. Now we have much bigger computers and we have databases of millions of relational facts, many of which are of the form A, R, B. A has relationship R to B. We could imagine training a net to discover feature vector representations of A and R that allow it to predict the feature vector representation of B. If we did that, it would be a very good way of cleaning a database. It wouldn't necessarily be able to make perfect predictions, but it could find things in the database that it thought were highly implausible. So if the database contained information like, for example, Bach was born in 1902, it could probably realize that was wrong because Bach's a much older kind of person and everything else he's related to is much older than 1902. Instead of actually using the first 2 terms to predict the third term, we could use the whole set of terms, 3 of them in this case, but possibly more, and predict the probability that the fact is correct. To train a net to do that, we'd need examples of a whole bunch of correct facts, and we'd ask it to give a high output. We'd also need a good source of incorrect facts, and we'd ask it to give a low output when we told it something that was false. We're now going to talk a little bit about an issue that's of interest to cognitive scientists, but may not be of much interest to engineers. So if you're an engineer, you can just ignore this video. In cognitive science, there's been a debate going on for nearly 100 years about the relationship between feature vector representations of concepts and representations of concepts via their relations to other concepts. And the learning algorithm we've just seen for family trees has a lot to say about that debate. We're now going to make a brief diversion into cognitive science. There's been a long debate between 2 rival theories of what it means to have a concept. The feature theory says a concept is a big set of semantic features. This is good for explaining similarities between concepts, and it's convenient for things like machine learning because we like to deal with vectors of activities. The structuralist theory says that the meaning of a concept lies in its relationships to other concepts. So conceptual knowledge is best expressed not as a big vector, but as a relational graph. In the early 1970s, Marvin Minsky used the limitations of perceptrons as evidence against feature vectors and in favour of relational graph representations. My belief is that both sides in this debate are wrong, because both sides believe that the 2 theories are rivals, and they're not rivals at all. A neural net can use vectors of semantic features to implement a relational graph. In the neural network that learns family trees, we can think of explicit inference as I give you person 1 and I give you a relationship and you tell me person 2. And to arrive at that conclusion, the neural net doesn't follow a whole bunch of rules of inference. It just passes information forwards through the net. As far as the neural net is concerned, the answer is intuitively obvious. Now if you look at the details of what's happening, there's lots of probabilistic features that are influencing each other. We call these microfeatures to sort of emphasize they're not like explicit conscious features. in a real brain there might be millions of them and millions of interactions, and as a result of all these interactions we can make one step of explicit inference. And that's what we believe is involved in just seeing the answer to something. There are no intervening conscious steps, but nevertheless there's a lot of computation going on in the interactions of neurons. So we may use explicit rules for conscious deliberate reasoning, but a lot of our common sense reasoning, particularly analogical reasoning, works by just seeing the answer, with no conscious intervening steps. And even when we do conscious reasoning, we have to have some way of just seeing which rules apply in order to avoid an infinite regress. So many people, when they think about implementing a relational graph in a neural net, just assume that you should make a neuron correspond to a node in the relational graph and a connection between two neurons correspond to a binary relationship. But this method doesn't work. For a start, the relationships come in different flavours. There's different kinds of relationship, like mother of or aunt of. And a connection in a neural net only has a strength. It doesn't come in different types. Also, we need to deal with ternary relationships, like A is between B and C. We still don't know for sure the right way to implement relational knowledge in a neural net. But it seems very probable that many neurons are used for representing each of the concepts we know, and each of those neurons is probably involved in dealing with many different concepts. This is called a distributed representation. It's a many-to-many mapping between concepts and neurons. In this video, we're going to look at the softmax output function. This is a way of forcing the outputs of a neural network to sum to 1 so that they can represent a probability distribution across discrete mutually exclusive alternatives. Before we get back to the issue of how we learn feature vectors to represent words, we're going to have one more digression. This time it's a technical diversion. So far I've talked about using a squared error measure for training a neural net, and for linear neurons that's a very sensible thing to do. But the squared error measure has some drawbacks. If, for example, the desired output is a 1, so you have a target of 1, and the actual output of a neuron is 1 billionth, then there's almost no gradient to allow a logistic unit to change. It's way out on a plateau where the slope is almost exactly horizontal, and so it will take a very, very long time to change its weights, even though it's making almost as big an error as it's possible to make. Also, if we're trying to assign probabilities to mutually exclusive class labels, we know that the output should sum to 1. Any answer in which we say the probability that it's an A is 3/4 and the probability that it's a B is also 3/4 is just a crazy answer. And we ought to tell the network that information. We shouldn't deprive it of the knowledge that these are mutually exclusive answers. So the question is there a different cost function that will work better? Is there a way of telling it that these are mutually exclusive and then using an appropriate cost function? The answer, of course, is that there is. What we need to do is force the outputs of the neural net to represent a probability distribution across discrete alternatives, if that's what we plan to use them for. The way we do this is by using something called a softmax. It's a kind of soft continuous version of the maximum function. So the way the units in a softmax group work is that they each receive some total input that they've accumulated from the layer below. That's Zi for the ith unit, and that's called the logit. And then they give an output Yi that doesn't just depend on their own Zi. It depends on the Z's accumulated by their rivals as well. So we say that the output of the ith neuron is e to the Zi divided by the sum over that same quantity for all the different neurons in the softmax group. And because the bottom line of that equation is the sum of the top line over all possibilities, we know that when you add over all possibilities you'll get 1. that is, the sum of all the yi's, must come to 1. What's more, the yi's have to lie between 0 and 1. So we've forced the yi's to represent a probability distribution over mutually exclusive alternatives, just by using that softmax equation. The softmax equation has a nice simple derivative. If you ask about how the yi changes as you change the zi, that obviously depends on all the other z's. But then the yi itself depends on all the other z's. And it turns out that you get a nice simple form, just like you do for the logistic unit, where the derivative of the output with respect to the input for an individual neuron in a softmax group is just yi times 1 minus yi. It's not totally trivial to derive that. If you try differentiating the equation above, you must remember that things turn up in that normalization term on the bottom row. It's very easy to forget those terms and get the wrong answer. Now the question is, if we're using a softmax group for the outputs, what's the right cost function? And the answer, as usual, is that the most appropriate cost function is the negative log probability of the correct answer. That is, we want to maximize the log probability of getting the answer right. So if one of the target values is a 1 and the remaining ones are 0, then we simply sum over all possible answers. We put zeros in front of all the wrong answers, and we put 1 in front of the right answer, and that gets us the negative log probability of the correct answer, as you can see in the equation. That's called the cross-entropy cost function. It has a nice property that it has a very big gradient when the target value is 1 and the output is almost 0. You can see that by considering a couple of cases. So a value of 1 in a million is much better than a value of 1 in a billion, even though it differs by less than a millionth. So when you make the output value increase by less than 1 millionth, the value of C improves by a lot. That means there's a very, very steep gradient for C. One way of seeing why a value of 1 in a million is much better than a value of 1 in a billion, if the correct answer is 1, is that if you believed the 1 in a million, you'd be willing to bet at odds of 1 in a million, and you'd lose $1 million. If you thought the answer was 1 in a billion, you'd lose $1 billion making the same bet. So we get a nice property that that cost function, C, has a very steep derivative when the answer is very wrong, and that exactly balances the fact that the way in which the output changes as you change the input, dy by dz, is very flat when the answer is very wrong. And when you multiply the two together to get the derivative of the cross-entropy with respect to the logit going into output unit I, you use the chain rule. So that derivative is how fast the cost function changes as you change the output of a unit times how fast the output of the unit changes as you change zi. And notice we need to add up across all the j's, because when you change zi, the output of all the different units changes. The result is just the actual output minus the target output. And you can see that when the actual and target outputs are very different, that has a slope of 1 or minus 1, and the slope is never bigger than 1 or minus 1. But the slope never gets small until the two things are pretty much the same. In other words, you're getting pretty much the right answer. In this video, we're going to look at a practical use for feature vectors that represent words. The use is in speech recognition systems, where having a good idea of what somebody might say next is very helpful in recognizing the sounds they make. We're now going to see an important practical use for feature vectors that describe words. When we're trying to do speech recognition, it's impossible to identify phonemes perfectly in noisy speech. the acoustic input just isn't good enough. It's often ambiguous. There may be several different words that fit the acoustic signal equally well. We don't notice this a lot of the time because we're so good at using the meaning of the utterance to hear the right words. So if I read the next comment on the slide, I would say, we do this unconsciously when we recognise speech. And you would hear, we do this unconsciously when we recognise speech. You can actually hear the slight difference between recognise speech and recognise speech. But if you're expecting recognise speech, particularly if there's noise around, you wouldn't hear recognise speech. Okay. So we're very good at doing this. We do it all the time and we do it unconsciously. That means that speech recognisers have to know which words are likely to come next and which are not. Fortunately, words can be predicted quite well without having a full understanding of what's being said. So there's a standard method for predicting the probabilities of the various words that might come next. It's called the trigram method. You take a huge amount of text and you count the frequencies of all triples of words. Then you use these frequencies to make bets on the relative probabilities of the next word given the previous two words. So if we've heard the words A and B, we can look at the counts that we have in our huge body of text for the sequence ABC and the sequence ABD. We can say that the relative probability that the third word will be C versus the third word will be D is given by the ratio of the two counts, ABC and ABD. Until very recently, this was the state-of-the-art method for getting the probability of the next word to help out the speech recognizer. We can't use much bigger context than two previous words because there are just too many possibilities to store, and if we did use bigger contexts, the counts would be mostly zero. Even for two-word contexts, there's many contexts that you will never have heard. For example, if I say dinosaur pizza, that's probably a string of two words that you've never heard before. For cases like that, we have to back off to individual words. So after dinosaur pizza, you predict the next word by just seeing what's likely to come after the word pizza, because you've never heard dinosaur pizza before. What you mustn't do is say that probabilities are zero just because you haven't seen an example. That's clearly not true. Now, the trigram model fails to use a lot of obvious information that will help you predict the next word. Suppose, for example, you have seen the sentence, "The cat got squashed in the yard on Friday." That should help you predict the words in the sentence, "The dog got flattened in the yard on Monday." In particular, the trigram model doesn't understand the similarities between words, like cat and dog, or squashed and flattened, or garden and yard, or Friday and Monday. So it can't use past experience with one of those words to help it with the other one. To overcome this limitation, what we need to do is convert the words into a vector of semantic and syntactic features and use the features of previous words to predict the features of the next word. Using a feature representation allows us to use much bigger contexts that contain many more words, for example 10 previous words. Yoshua Bengio pioneered this approach for language models, and his initial network for doing this looks rather familiar. It is actually very similar to the family trees network, it's just applied to a real problem and it's much bigger. So at the bottom you can think of us as putting in the index of a word, and you could think of that as a set of neurons of which just one is on, and then the weights from that on neuron will determine the pattern of activity in the next hidden layer. And so the weights from the active neuron in the bottom layer will give you the pattern of activity in the layer that has the distributed representation of the word, that is its feature vector. But this is just equivalent to saying you do table lookup. You have a stored feature vector for each word, and with learning you modify that feature vector, which is exactly equivalent to modifying the weights coming from a single active input unit. After getting distributed representations of a few previous words, I've only shown 2 here, but he would typically use, say, 5, you can then use those distributed representations via a hidden layer to predict via a huge softmax what the probabilities are for all the various words that might come next. One extra refinement that makes it work better is to use skip layer connections that go straight from the input words to the output words, because the individual input words are individually quite informative about what the output word might be. Bengio's model was actually slightly worse than trigrams at predicting the next word, but it was in the same ballpark, and if you combined it with trigrams, it improved things. Since then, these language models that use feature vectors for words have been improved considerably, and they're now considerably better than trigram models. One problem with having a big softmax output layer is that you might have to deal with 100,000 different output words, because typically in these language models, the plural of a word is a different word from the singular, and the various different tenses of a verb are different words from other tenses. So each unit in the last hidden layer of the net might have to have 100,000 outgoing weights, and that means we can only afford to have a few units there before we start overfitting. That's not necessarily true. We might have a huge number of training cases. So some organisation like Google might have so much training data that it can afford to have a very big softmax layer. We could try and make the last hidden layer small so we don't need too many weights, but then we have the problem that we have to get the 100,000 probabilities of the various words that might come next fairly accurately right. It's not just the big probabilities we need. A very large number of words will have small probabilities, and the small probabilities are often relevant. It might be that the speech recognizer has to decide whether it's two different rare words, and then it's very relevant which of those is more common in the context, even though both of them are pretty unlikely. The question is there a better way to deal with such a large number of outputs? And we'll see several different ways of doing that in the next video. In this video, we're going to look at various ways to avoid having to use 100,000 different output units in a softmax if we want to get probabilities for 100,000 different words. At the end of the video, I'll show an example of the words or the word representations that are learned by a particular method. To see what these representations look like, what we do is we embed them in a two-dimensional space, and then we can see which words have extremely similar representations. That gives us a feel for what the neural network has been able to learn just in trying to predict the next word, or perhaps the middle word of a string of words. So one way to avoid having 100,000 different output units is to use a serial architecture. We put in the context words as before, but now we also put in a candidate for the next word in the same way as the context words. Then we go forwards through the net, and what we output is a score for how good that candidate word is in that context. Of course, we have to run forwards through this net many, many times, but most of the work only needs to be done once. So the inputs from the context to that big hidden layer are the same for every different candidate word. The only bit we need to run for each candidate word is the inputs coming from the candidate word and the final output to the score. And of course, that doesn't have many weights in it. So we try all the candidate words one at a time, and by putting in the word as a candidate at the bottom, we're able to use the learned feature vector for that candidate word that we learned when it was a context word. So we can have the same representation of the word when it's part of the context and when it's a candidate for the next word that we're trying to predict. Learning in the serial architecture works in the following way. We first compute the score for each possible candidate word, and then we put all those scores, which we computed sequentially, into a big softmax to get word probabilities. Now the difference between the word probabilities and their target probabilities, which is normally 1 for the correct word and 0 for everything else, gives us the cross-entropy error derivatives, and we use those derivatives to change the weights in such a way that we raise the score for the correct candidate and we lower the scores for all of its high-scoring rivals. We can save a lot of time in this architecture if instead of considering all possible candidate words, we only consider a small set, perhaps candidate words suggested by some other predictor. For example, we could use the neural net to revise the probabilities of the words that the trigram model thinks are likely. A different way to avoid a great big softmax is to structure the words into a tree. So we arrange all of the words in a binary tree with the words as its leaves. We then use the context of previous words to generate a prediction vector v. We compare that prediction vector with a vector that we learn for each node of the tree. The way we do the comparison is by taking a scalar product of the prediction vector and the vector that we've learned for the node of the tree, and then we apply the logistic function to that scalar product, and that will give us the probability of taking the right branch in the tree, and 1 minus that gives us the probability of taking the left branch in the tree. So the tree looks like this, and if that sigma is the logistic function, you can see at the top of the tree that we take the logistic of the prediction vector times the vector that we've learned ui at the top node, and that tells us the probability of taking the right branch, and conversely we take the left branch with 1 minus that probability. And so on, all the way down the tree to the word we want. So when we're learning, we use our context to get a prediction vector. We use quite a simple neural network for this work, where we take the feature vector for each word, and those feature vectors directly contribute evidence in favour of a prediction vector. We simply add up the evidence contributed by those feature vectors, and that gives us the prediction vector. That prediction vector then gets compared with the vectors that have been learned for all the nodes in the tree on the path to the correct next word. So that will be nodes I, J and M in this tree. That red path shows you the path to the word that actually occurred next. And those are the only nodes we need to consider during learning. What we know is that we'd like the probability of predicting that word to be as high as possible, and so we'd like the probability of taking that path to be as high as possible. So we'd like the product of the probabilities on the individual elements of that path to be as high as possible, and that means we'd like the sum of their log probabilities to be high. So we benefit from a nice decomposition here, that when we try and maximize the probability of picking the correct target word, we're really trying to maximize the sum of the log probabilities of taking all the branches on the path that leads to that target word. So during learning, we only need to consider the nodes on that correct path, and that's a huge win. That's exponentially fewer nodes than considering all of the nodes. So it's log to the base 2 of n instead of n. For each of those nodes, we know the correct branch because we know what the next word is. We know the current probability of taking that branch by comparing the prediction vector with the learned vector at the node. And so we can get derivatives for learning both the prediction vector v and the learned vector at that node, u. This makes the training hundreds of times faster. Unfortunately, it's still slow at test time. At test time, you need to know the probabilities of many words to help the speech recognizer, and so you can't just consider one path. There's a much simpler way to learn feature vectors for words. This is work by Collobert and Weston, and what they did was learned feature vectors for words and then showed that the feature vectors they learned were very good for a whole bunch of different natural language processing tasks. They're not trying to predict the next word, they're just trying to get good feature vectors for words. And so they use both the past context and the future context. So they look at a window of 11 words, 5 in the past and 5 in the future, and in the middle of that window they put either the correct word, the one that actually occurred in the text, or a random word. And then they train a neural net to produce an output that's high if it's a correct word and low if it's a random word. The neural net works the same way as before. We map the individual words to feature vectors, these word codes, and then we use the feature vectors in the neural net, possibly with more layers in the neural net, to try and predict whether this is the right or wrong word for that context. So what they're really doing is judging whether the middle word is an appropriate word for the 5-word context on either side of it. They trained this up on about 600 million examples from Wikipedia, and they showed that the vectors they get are good for a variety of different natural language processing tasks. One way of getting a sense of the vectors that they learned for words is to display the vectors in a 2-dimensional map. What we want to do is lay out the word vectors in such a way that very similar vectors are very close to one another. So then you'll discover what words the neural network thinks have similar meanings. We're going to use a multi-scale method called t-SNE. You can look up t-SNE on Google and discover how it works if you want. And t-SNE is able, in addition to putting very similar words close to each other, it's also able to put similar clusters close to each other. So it gives you structure at many different scales. What we see is that the learned feature vectors capture lots of subtle semantic distinctions, and they do this just by looking at strings of words from Wikipedia. Nobody tells them anything other than the fact that these 11 words occurred in a string. There's no extra supervision. What's remarkable is that contextual information, the fact that these words occurred together, tells you an awful lot about what the word means. In fact, some people think that's the main way we learn the meaning of words. So here's an example. If I give you a sentence with a word you've never heard before, like she scrommed him with the frying pan, from that one sentence you already have a pretty good idea of what scrommed means. It's conceivable that she was trying to impress him with her cooking skills, and so scrommed means impressed or something like that, but probably it means something like walloped. So here's part of a 2-dimensional map in which we laid out the 2,500 commonest words, and you'll see this part of the map is all about games. Not only that, it's got similar kinds of words together. So matches and games and races are together. It's got players and teams and clubs together. It's got the things you win at games together, like cups and bowls and medals and prizes. It's got different kinds of games together. It's done a very good job of taking these words to do with games and finding out which ones are very similar in meaning. And because it's using very similar feature vectors for those, it can, in any natural language processing task, say that if one word was a good word for that context, the other word's probably also a pretty good word for that context. Here's another part of the map. This part of the map is entirely about places. At the top it has US states. Under that it has some cities, mainly ones in North America. And under that other cities. Then it has some countries. So if you look at the cities, this one is clearly Cambridge, and underneath Cambridge there's something else that's very similar to Cambridge. Here we see that it's put Toronto with Detroit and Ontario and Boston. Toronto's in English-speaking Canada. And it's put Quebec, which is in French-speaking Canada, with Berlin and Paris. If we look at the bottom, we can see that it thinks Iraq is pretty similar to Vietnam. Here's another example. If you look here, these are adverbs, and it's understood that likely and probably and possibly and perhaps all mean very similar things. It's also understood that entirely, completely, fully and greatly have very similar meanings. And it's understood various other kinds of similarity, for example, which and that, or whom and what, or how and whether and why.